Good morning, a little bit later than intended, but good morning and welcome to the second day of this HPP workshop for high performance computing for neuroscience. I am Alberto. I've been working for a little bit over 3 years at CSCS, the Swiss National Supercomputing Center, which is one of the institutions, partner institutions, along with the Jülich Supercomputing Center and other 3 European supercomputing centers offering computing and storage infrastructure for the HPP project. And also as part of the Phoenix research infrastructure, if you are familiar with that. So in the first day, you were taught a lot about Python, how to access scientific modules, how to do some numerical computations with Python, all cool stuff. But today, we move into the defining part of this workshop, and so it falls upon me the honor and the responsibility to lead you into the wonderland of high-performance computing. So how do I intend to organize this session? I start with explaining what is HPC and why do we need it. Call it the what and why, because I really didn't want to call it introduction, because the introduction of the introduction would have been awkward. Then I'll give you a very high-level view of the architecture of HPC systems, around more or less 20 minutes. I'll try to cover all the big pieces moving around and what makes a supercomputer a usable infrastructure for useful research. And then I'll give you a tutorial or a live demo of what it's like to use a supercomputer from a user perspective, covering 2 main topics. The first one is environment modules. How do we modify our session environment for the things we want to do, and then how to submit jobs. And then the last part, we'll have some time for some hands-on exercises. So that's why you have been toiling over getting these SSH keys done. So you can log into Eureka. It's one of the supercomputers. You have probably seen it yesterday from the foyer during the breaks, and have a first taste of what it's like to use one of these machines. The session material, so these slides, the handout that I also have printed, the handout for the exercises and some materials, so you won't be needed, but if in case you need any reference, it's in the GitLab repository of the workshop that you have also been using yesterday. It's in the Introduction to HPC subfolder. It wasn't there yesterday because I uploaded the material yesterday evening. Okay, so let's move on. What is high-performance computing? So this is my definition. I didn't get it from Wikipedia or anything, but I just try to be as general as possible. HPC can be defined as leveraging special purpose solutions in all aspects of making a computation, starting from the hardware, from processors, network, and storage, up to the software level for the operating system, libraries, and then all the way to the user applications, having special dedicated solutions to perform computations which are orders of magnitude, sometimes bigger than those that can be done on mainstream computers, on personal computers, or even workstations. In terms, how are they bigger? In terms of processing speed, getting things done sooner, and data size. How much stuff are we actually computing. And data size regards both to input and output, so also the size of the results. Sometimes both are huge, sometimes only one of those. But so why do we need all this stuff? Is it really useful? Well, yes. In the context of science, there are some cases where it is actually impossible to create a physical experiment. Think about cosmology. It's a little bit tricky to recreate the entire universe in a laboratory just to study how it expanded after the Big Bang. Or climate. It is also complicated to recreate the entire Earth system in a laboratory with a physical experiment to study how the climate would evolve on a very precise scale over the next 50 to 100 years. And maybe we also want the results before that. So this is why increasingly physical experiments are getting replaced by high resolution, high performance simulations. And there is also it's a kind of a marketing punchline, but you may start hearing more and more about simulation becoming the third pillar of science alongside theory and experiments. And even when it's not just about replacing a physical experiment, but also problems that are already formulated as computations, as computational problems. Some of them are completely intractable on normal computers. Think about in chemistry and material science, figuring out how very complex molecules interact with them, how proteins fold. Life sciences, we have heard from Abigail in the very first session yesterday, how complex are neurological systems, the brain, the synapses, all the stuff that is there to study. And then processing an ever-increasing amount of data from an ever-increasing amount of sensors all over us, all over the world. So, and these are just a few examples. There are many more fields, and there are increasingly more by the day that resort to high-performance computing to actually get some innovation and some discovery done. And some of these issues, some of these fields are becoming so critical that even governments and political institutions are identifying now high-performance computing as a key strategical capability for the continuing competitiveness in science and technology. This is one of the reasons why US and China are locked in this battle on who can build the biggest, fastest computer, and is also the reason why Europe is now starting billion euros projects for developing a European indigenous supercomputing expertise. So this is all well and good, but this is still conceptual. More concretely, how do we do HPC? Well, we do it with very special tools. We call them supercomputers. And as I said, as the computing and simulation gathers more and more consideration as a scientific phase, these machines, these supercomputers, are also increasingly appreciated as instruments of discovery. Think like more of a regular laboratory instrument, like a microscope or something. They are kind of getting there in that sign of. They're getting that kind of consideration. So there is also not a strict definition of what a supercomputer is. Generally, we can say it's a system with a significantly higher performance compared to a commonly available system, like even a workstation, or even more so of a personal computer or a laptop. The performance of these systems is usually measured in flops, and that stands for floating point operations per second. So basically, it's the amount of additions or multiplications between two floating point numbers. If you're not familiar with floating point numbers, they're basically a standard representation of decimal numbers and rational numbers. So basically, you count up how one of these machines, how many operations can it do for a given amount of time, and you come up with the representations. The best supercomputers today can achieve more than 1 petaflops, more than 10 to the 15 floating point operations in a second. That's quite a lot. For example, this one in the picture here is PITS-DINT, is the flagship system for of CSCS, and it's also one of the machines in the Phoenix research infrastructure, and it's also part of the. It's also open to HBP researchers. This machine can do 21 petaflops in optimal conditions. If you compare it to a laptop with a mainstream CPU and integrated GPU, it's about 20 gigaflops. So this thing here is 1 million times more powerful on paper, and in reality even more than a regular computer. That's a lot of research you can get done, more than with a usual outfitting. The problem is that these kind of machines consume power in the order of the megawatts, and as you can see from the picture, they tend to get pretty big. I think you also had the impression yesterday watching the machine room from above. But actually, while they are more powerful than a normal computer, they're not conceptually the same. They are very different. For starters, they are not monolithical machines. It's not just one single entity. There is not a huge processor that is responsible for doing all the magic. In fact, the supercomputers today are composite machines. They adopt an architecture called cluster computers. What this means is that in reality, they are modular and tightly connected sets of smaller computers that are able to work together very effectively, and they are presented as a single entity. Starting from the system level, the system is usually composed of a series of cabinets. As you can see from the picture, they are like closets, more or less. These cabinets can be easily the height of a person or a little bit more. Inside the cabinets, there are so-called the blades. There are these kind of trays that fit inside the cabinets, either horizontally or vertically. And a blade usually houses one or more nodes. The nodes are the atomic components of a supercomputer. And conceptually, they are the closest thing to a normal computer. They have their own processor, their own memory, and their own operating system. So you can use nodes individually or together, and all this infrastructure is about making them work, making, let's say, the whole bigger than the sum of the single parts. But why do we need all this complicated stuff? Why is a system constructed this way? Well, the main reason is, and And the greatest reason is efficiency. Efficiency in many fields, in many aspects. Space efficiency. With these structures, nodes can be packed together more effectively. We can have, and because as you can see, systems are already pretty big. We need thousands of these nodes in order to build a supercomputer, and we don't want to build a skyscraper or something huge every time we need a new machine. We want it to be as compact as possible. Thermal, electrical, and cost efficiency. By eliminating redundant parts and only adding the single components that are needed for the computations. So for example, here the nodes, as I said, only have a CPU and the memory and all the other things that you take that you have to consider when you build a personal computer. They're just contained in a common infrastructure inside the cabinet or the blade. And the reason for eliminating the redundancy of the non-compute critical parts is because if they're not there, you don't have to cool them, you don't have to give them power, and you do not have to pay for them. Yeah, network efficiency. Since the nodes are packed together better, there is less distance to travel through a network. So the communication happens faster, and it's also easier to connect them. And then maintenance. This is a modular architecture. When something breaks, you can take out a blade without affecting the functioning of the rest of the machine or an entire cabinet, because you want to make them, you want to let them run as much as possible. So it's also important to maintain it in an effective way. Okay, so let's stay at the very lowest level. Let's talk about what are the key components inside a node. What makes the supercomputer tick? And let's talk about the processors, the processing hardware. So generally, the processors for supercomputers are more capable counterparts of normal consumer processors. While they have similar architectures, they come with way more cores. We're talking about 10, at least 10 cores. 20 or 30 cores are nothing to yell about today. It's pretty common in modern supercomputers compared to the 4 or 8 cores that you get on a laptop usually. They have bigger caches. Caches are fast and temporary memory spaces very close to the processors. They allow you to reuse data effectively without going to read to the main memory every time. And often we also have multiple CPUs per node. So you can have nodes with 70 or even more threads available. Compare that with the advertising for the latest personal computers. There's 8 cores, 16 cores, 70, 100. And nodes also have very generous amount of RAMs, of memory. We can 128 or 256, it's not a problem. You also usually there are also specialized big memory nodes with up to 1 terabyte of RAM per node. So maybe you noticed that, yeah, is there a question? No, okay. By the way, you can freely ask questions whenever you want. You can stop me. I have no problem with that. So maybe if you're familiar with computers, you may have noticed that I didn't make a point about one key metric that is usually associated with processor performance, and that is frequency. That's a thing you hear a lot about. 2 gigahertz, 3 gigahertz, 4. Why is not frequency considered here as key factor for supercomputers? Well, for this reason. It's called Denner scaling. So basically what happened is that there is a physical limit for how much current you can get inside a processor core, and that derives on how much frequency you can run that processor. And we have reached that limit at about, depends on the architecture, between 3 and 4 gigahertz. We have reached that limit in 2005. So the key, this is a graph of the microprocessor data over the last 40 years. The key metrics, the key trends are the orange one, the number of transistors, the green, which is the frequency, and the black, the number of cores. So in 2005, we've reached the maximum frequency we could give to a single processor core. But what happens? The innovations of semiconductor manufacturing kept pushing the number of transistors possible in a processor upwards. They continue to progress. So what did microprocessor designer do? They started bumping up the number of cores. So in HPC, you rely more on a greater number of cores, so parallelism is increasingly important compared to huge frequencies, because really we cannot push them further than this. So yeah, they basically utilize the excess transistors to add more core instead of pushing the performance, instead of pushing the frequency up. But eventually, for the performance-hungry customers everywhere, from science, industry, research, military, whatever, even the increase in efficiency from the CPUs was not enough. And so someone came up with the idea of actually accelerators, which, no, that's a little bit wrong. Accelerators were already a thing in the 70s, but there has been a revival starting from the end of the last decade. Accelerators are devices that work as coprocessor. They complement the main CPU by offloading specific computing tasks. So they make a trade-off in programmability and flexibility in order to obtain higher performance. They support a limited amount of, they effectively support a reduced amount of computing patterns. They are effective only in given scenarios, but they're much better at it. They usually feature thousands of cores. For these reasons, they are called many-core architectures instead of tens of cores, which are usually are identified with multi-core term. And the greater part of the chip of an accelerator is usually dedicated to the computation, more transistors, less program control. So by the way, you streamline how the program should be written, and then you can dedicate more transistors to actually making operations. Some examples of accelerators, well, the poster childs are undeniably GPUs, especially NVIDIA GPUs. You may have heard them used as accelerators. Eureka here has also a partition with some GPUs. You may have heard also of the Intel Xeon Phi, many-core processor or coprocessor from Intel. Now it's discontinued. FPGAs, field programmable gate arrays. And also, now we're seeing the rise of deep learning, artificial intelligence, and linear algebra specific chips, since the market and the hype around machine learning, artificial intelligence is so big, and It's actually based on a lot of matrix multiplications. We're seeing also a rise on these dedicated chips. So to give you an idea how effective an accelerator can be, this is some data taken from the latest list of the top 500 supercomputers in the world. It's issued every 6 months, so twice a year. We have the #1 system in the world, Summit, with NVIDIA GPUs. We have Frontera, which is a freshly debuted system, #5, with only CPUs. Here I have put Pittsdienst, which is the #1 supercomputer in Europe, also using GPUs. And as an example, Sequoia, which is another system not using accelerators. And you can see from the efficiency, so how much flops, how much computations can we do with a single watt for unit of power that we have to give to the machine. Well, the efficiency of the computers using GPUs as accelerators and the ones using traditional CPUs is pretty stark. So it's also reflected in, and it's also been reflecting in the upper levels of computers. These are actually, there are very few top 10 supercomputers in the world which do not have accelerators, or actually even very few top 50, I think. Okay, so this is just about what we can get on the node to make them work at the lowest level. So we've gone down from the system level down to the node level, and then now let's get back up. So let's now consider, for example, supercomputer. We have a bunch of nodes, which my amazing drawing skills represent as gray squares. Let's say we deploy these nodes. We had some CPUs, two per node. Why not? We had the RAM. Let's add the GPU for good measure, because why not? Now what? Oh, we actually need them to talk to each other. We need to. They need to collaborate, because that's what makes a supercomputer so superior. So we need an interconnect. The interconnect is actually one of the key components that makes HPC systems what they are. They have to be designed to move around lots of data very fast, because you cannot have super powerful nodes that actually communicate, I don't know, 1 kilobyte per second between them, because then you can only push the supercomputer as far as your network allows you to go. So it has to be a balanced design. You can compute what you can exchange, and you regulate on sort of that. And for this reason, since the interconnect is so critical, there are some dedicated solutions for that. A high band, an interconnect for HPC will have bandwidth in the order of hundreds of gigabits per second. Latencies, so basically how much you have to wait for transactions to respond or to go through, in the order of microseconds. Topology is very important, so basically the pattern with which you connect the nodes between them. So here, this is an extremely abstract representation I just connected in a square grid. But in reality, what happens is that systems use either a tree topology, and some designs are based upon very fancy graphs, like the, I don't know, dragonfly topologies, torus topologies. Designers have really gone wild in order to make the topology more efficient as possible, both in terms of what is the shortest distance, overall distance a signal has to go through when I move data around the computer and minimize the number of hops I have to go through in order to propagate the data. These topologies are implemented with a variety of technologies. Ethernet is the one that's also more known to the general audience. We use it every day in our homes to connect the Ethernet cables for the routers, or also at the workplace. InfiniBand is a technology born specifically for high-performance networks. It's a little bit harder to I think it started with a definite performance advantage over Ethernet, but now Ethernet is catching up. And InfiniBand had a different low-level model. It's not something that is exposed to the users, but a low level is a little bit more complicated. And then we have proprietary interconnects that you only find in specific vendors, system from specific vendors. We have Cray. It's a very famous supercomputer maker with their Gemini or Aries interconnects. Intel has their OmniPath, and Fujitsu has developed the Tofu interconnect. Nothing to do with food. It's about torus fusion, so it's based upon something more complex than this. Okay. So we have our cluster. We have our high-performance components, CPU, GPU, good interconnect. There's a lot of parallelism available in this setup because, as we have said, each node, each gray box is a computer on its own. Inside that, every CPU has tens of cores. And then every GPU has thousands of cores. So there are actually a lot of things that we can do at the same time with a setup like this. How do we leverage it? That's a good question. And that's what parallel programming is all about. We have to think about how to apply our problem into such an architecture. So, and we have to think in basically two big areas. The first is how are the different processes going to communicate between them? And the second one is how are we going to decompose our problem? Speaking about process communication, we can distinguish shared memory communications, where basically the processes all access the same memory space, and so whatever you write in that memory can be read by another process without anything explicit, but it has its pitfalls. Some shared memory programming models are OpenMP. I don't know if, Jan, you will mention something about that. OpenMP, no? No, okay. Right, you got it. So CUDA, the programming model for GPUs, they're all shared memory. Then we have, for example, message passing, which basically is another way of saying distributed memory parallelism. In this model, each process has its own private memory. So we have to explicitly communicate the data between one process to the other. That's why it's called message passing. And the standard way of doing this is through a standard called MPI, the message passing interface. And that's what Jan will talk a lot during his lecture after lunch, 13:30, a lot of MPI and figuring out how to pass these messages, these packets between the processes. There is another option. It's called implicit communication, where basically the programmer does not specify anything and lets the compiler or the hardware decide how to manage everything. This is what you may have from a domain-specific language or from automatic parallelization tools, where you basically, okay, do it whatever you want. It's very handy, but usually it's not as optimal. You cannot squeeze everything as if you were telling exactly the program what to do, because no one knows the application better than the programmer. No amount of software or hardware. Going over problem decomposition, we can choose a few ways of how to decompose our problem into a parallel program. We can choose task parallelism, where we perform different operations on the same data. Data parallelism, where we perform the same operation on different data. This is sometimes also called vectorization, and it's how GPUs work. You take a bunch of data and you apply the same operation over a vector or a matrix. For example, for every different element, you have a different thread doing the same operation over it. And then we also have implicit parallelism, which is basically the counterpart of implicit communication. And for a deep dive on all of this beautiful stuff, Yannis will give you the full treatment after lunch, as I said. Okay, so we have our computing cluster, very good. We kind of have an idea of how to use it, but we need some essential supporting structures. The supercomputer is not just a computing cluster, is an elaboration cluster. First, we need what is called a login node, because usually users do not access the compute nodes directly. Users log into a separate computer called in fact the login node, where you basically reside, and from the logging node you instruct the compute nodes to carry out your tasks and your applications. And also we need some big fat storage, because the compute nodes are so essential, so to the bone, that they have very limited disk space on them. Effectively, some systems also do not have disks on the compute nodes. They are called diskless nodes. And we really need a huge amount of storage for managing all the huge inputs and huge results that we mentioned at the start of the talk, and to distribute them effectively or gather them effectively across all the cluster. That's why we have HPC-specific storage, which are based upon parallel file systems. Parallel file systems are software components and their accompanying hardware, which are designed to store data across multiple servers at the same time. And this allows them to scale very effectively, to be very performant in retrieving lots of data, because they do it at the same time, and also handling concurrent access or reads when many users require same kind of data. Some example of parallel file system is GPFS, is a general purpose, is very used. I think the storage infrastructure here at JSC is mainly based around GPFS. And another popular solution is Lustre. I'm not a storage expert. I think Lustre tends to scale better, but it has problems when handling a large amount of small files and when the file system is occupied too much. So you have a significant performance degradation when that happens. So there are advantages, but they have to be managed. Very important thing from a user perspective. Every computing site configures and manages their storage systems independently. So it's essential to know the policies of the storage from your computing site in the terms of which file systems are available. Do you have a home? Do you have a scratch? Do you have a project storage? How many and what are those? What is the recommended usage? Which one should I use for long-term storage? Which one should I use as a staging ground for my computation because maybe it's connected better to the cluster? Quotas. I don't think any computing site will let you store an indefinite amount of data. You always have a quota for yourself or for your project. So it's definitely useful to know how much data you can get into the file system. And then how are the file systems connected to the clusters? Which ones have a faster connection? Which one is lower? And also, some file systems might not be visible on the same parts of the computer. For example, there are some file systems that are visible only to the login nodes. Some others may be visible only to the compute nodes. So useful information. And for JSC, this kind of information is reported on their website and for each supercomputer. But again, reference to Lina's lecture that will happen before this. Before. We're traveling in time. That will happen after my session. She will give you much more details about parallel file system and how to effectively manage data and move it around. Okay, that basically completes the architecture overview of the parts that form a supercomputer. And I will talk more about what it is like to use a computer from the user perspective and not about how to build it from a designer perspective.